Okay, we are. Oh, now we're live.
Now we're live.
Now we're live on episode 21 of a
21,
certain dots.
uncertain dots can drink. So
Let's see settings. I still don't know how to do this, so I'm probably gonna give up pretty quick.
try and find the link for people to join.
Yeah. They said it would be on your YouTube Live page. What is my YouTube Live page?
A YouTube Live page?
Yeah. Let's see. What if I put YouTube/live? Nope.
So I think maybe if you go to your YouTube page and yeah, they keep changing the layout of the YouTube stuff too. So I don't know.
Yeah, they do. That's for sure.
Yeah, what? They keep hiding things.
Live events. Enable live streaming. Oh, I just did. Okay, I don't know what that does. I agree. You can only do this once you start. Live now. Okay, there it is.
Yeah, I'm gonna throw the link on Twitter so people can come watch us argue about how to work Google software.
Okay, let's see if this works.
Live. Thrill to Chad and Rhett trying to debug web software. Now we'll see what we see. But
Now okay. On. Okay, let's see if that works. Okay.
all right.
So
So I don't know. So are you between classes?
yeah. So we last week finals was on Wednesday, and then right after that I went to Santa Monica to give a talk at the Rand Corporation, and then now I'm back. So I'm trying to catch up on blogging and stuff like that, but
Yeah, you got a couple of weeks or.
yeah, I don't really know. You'd think that's what my wife says. When do classes start? And I said, I don't know.
Sometime not too distant future.
Hopefully soon. It's probably soon, but not too soon. Not tomorrow. So
yeah. We're kind of late this year. We start the 10th, so
I think we're like August 20th ish.
Yeah.
But
do you guys teach on Labor Day?
that's a great question.
Probably, if you don't know the answer.
Yeah, I don't know. So, and I looked at my schedule, and I'm just teaching like labs. I'm like, oh, I wasn't paying attention to what I was and was not teaching. So,
And just doing labs isn't so bad.
the thing that it's a personal preference here. I really enjoy working with the chemistry and physics major classes, not the biology and the pre-med classes. Not that there's anything wrong with those people. It's just that these are the people that are going to be in the department, and so it's good to get to know them, and you'll see them for 4 years or whatever. And the other classes, they're usually seniors and they're on the way out. So
yeah, I definitely prefer the classes where it's you get to know people, you're gonna see them again. That's one of the nice perks of the job is getting to meet kids. And we do a pretty good job with making the department feel like a community for our majors, and so there are students around all the time and get to see them a lot and get to know them pretty well. So that's a nice feature.
So we have some things we can talk about. Do you want to talk about the impossible space drive, or do you want to talk about the Rosetta mission, or?
Well, the impossible space drive thing is I don't quite understand what's going on there. I think it's the same people that had the weird warp drive thing, and so somebody there must have some pull in NASA to get to keep doing this wacky stuff, and I don't really know what they're doing.
Well, I think that from what I understand, it's a small group of people that their job is to study wacky stuff. I mean, which is for NASA, I think that's a great idea, right? Put some people on these projects that could be crazy, but maybe they'll be awesome, and it's a low investment and possibly a high return.
Yeah.
So I mean, there's just a few people that's their job, just to check out these different perpetual motion machines of space, which is what I would call this, right?
Yeah, yeah, it's a strange thing. I mean, I went, I looked. I didn't read it real carefully, but I went through the report a little bit. And it's this weird mix of, of this. There's this like concluding sentence that talks about how we're really pushing against the quantum vacuum virtual plasma thing, which is a concatenation of four words that
Yeah, that was a problem right
you
there.
could find somewhere. But and then there's this like whole section on how you would use this to make a really fast trip to Mars. But the actual procedure section is that reads like it's written by somebody who is pretty sure this is this doesn't actually do anything, but is humoring somebody by running these tests.
I mean, when you get these results of super small values of force, I mean, it could be anything. There could be high currents in the wires going to the device interacting with the Earth's magnetic field, causing some torsion, right? I mean, it could be any number of things, because you're talking about tiny, tiny amounts of force. I mean, it could be attraction to me, so it could be a gravitational attraction.
Yeah, and you look at it, they did a total of like 5 tests of each of these objects. So and they say that it was cut short. They ran up against the test windows. They're still debugging the thing right up through the tests. They only did a handful of tests of it, but there's so many finicky things that go wrong with these that I mentioned in the blog post the one group that they have lead bricks piled near their torsion pendulum because there's a hill behind the physics building, and that balances out the gravitational force. But there's also the one, and I have a graph of it in the book. There's a group at MIT that did precision mass measurements with a cyclotron ion trap, and they found that their experiment worked best between like 1 and 4 in the morning because of the Boston subway. That when the subway train would go by, the current surge from that caused the magnetic field in their lab that would throw their results off. And so during the day, there's this plot of the magnetic field in the lab, and during the day it goes all over the place. And then at about 1 o'clock in the morning, when the trains stop running, it goes. It's a nice flat line, and then it goes crazy again at like 6. So
that reminds me of going to the LIGO observatory near here. They they have problems during logging season. So when they're cutting down logs around there, it's like, we just can't collect data because there's too many.
It's like, is that a gravity wave or a tree? So.
It's a bulldozer.
Yeah, and they have. That's why they have 2 of them, right? They put one in Washington State in the middle of nowhere, so that presumably the loggers aren't, they're not quantum entangled, so they're not simultaneously toppling trees next to both of those sites.
But the impossible drive, I think the interesting thing to look at. I mean, I think we both agree that it's probably not real. That's why it's called impossible. But the interesting thing is to look at how this news story propagated, right? Someone picked it up, and it's a great headline, right? You can get to Mars in 3 days. Impossible drive. NASA proved impossible drive.
Yeah.
And I think a lot of people just picked it up and ran with it, right, without having to really kind of contemplate the worthiness of the story.
Yeah, there are a whole bunch of these, space enthusiast networks and things that are often kind of credulous about these things, which, I think it. I haven't seen it in any like really big media things. Mostly what I've seen from the more mainstream people on Twitter and whatnot is people linking to physicists saying, "Yeah, that's not going to work."
Yeah.
So, but it's I don't know. It's interesting. It's a nice excuse to talk up the torsion pendulum experiments because I think those are really cool.
It's also, great to bring in ideas of, why we don't think this would work, and which is the same. Except it's a momentum version of the perpetual motion machine, right?
Yeah, basically.
So, and it doesn't mean that we can't find things like that to work. It's just that we have collected over a long period of time a lot of evidence, just like with energy. We have energy as conserved because that's what we've seen, not for some fundamental reason. It's just that's what we see. And when you find one thing that doesn't do that, it's kind of like, well, I don't know.
Yeah, it's an interesting point. Like a lot of you read a lot of pop science treatments of energy conservation, momentum conservation these days. They sort of end up starting from Noether's theorem, saying that symmetry says that there must be a conserved quantity that's because the laws of physics are translationally invariant, momentum must be conserved, and and that's true, and there's a mathematical elegance to that, and that's very nice, but like you said, there's 300 years of experimental tests, demonstrating with high precision that's actually the case. And most of those 300 years were before Noether did her work in the first place. So, it's worth remembering and reminding people that it's not just that we have this mathematical theory that says this can't work. It's we've got, going back to before Galileo, people showing that doing things that prove that momentum conservation works. And we're very confident that that's the case. Not only for philosophical reasons, but for concrete, practical, experimental ones.
I think that's one of the things I see students have a problem with. They're like, well, how do you derive Coulomb's law? I'm like, you can show that it agrees with other things, but originally it's not even derived. We're not even deriving conservation of energy. We can show that it agrees with these other principles, but it's an experimental thing on the most part. We make up this idea called energy, and it turns out to be conserved. But the experiment is the most important and the leading part of that.
Yeah, well, it's one of those things. It comes out of people playing around with. Once you get Newton's laws, people start you solve a bunch of problems, and this m times v squared just keeps showing up in lots of places, and that then people start to say, well, maybe this has some significance, and start working with that. I think Leibniz was one of the first to really start pushing the idea of what we now call kinetic energy as a thing, because when you start doing calculations, it's a quantity that shows up a lot, and maybe that's a thing that you should keep track of. The development of that's all pretty cool. But it is all comes out of observation and experiment.
So there's a question. Did you see that? Can you see there's a question?
No, we're
okay. Maybe you got to turn on your in the toolbar. There's like it's called questions. Okay, the question says basically 300 years of observation for macroscopic situations, but what about energy at the nano level?
Yeah, at the nano level, we've only been able to look at things at the nano level for a much shorter time. So that's only about 100 years. But again, there's lots and lots of observations of that. Pretty much every spectroscopy experiment that you do involves some test of conservation of energy, right? Because the color of the light that comes out depends on the energy difference between things. There was a point where, famously, Niels Bohr was willing to overthrow conservation of energy at one point in the late 20s because of the beta decay. You get this very broad continuous spectrum that you shouldn't get if if it's just one particle falling apart into two particles. So Bohr was willing to throw that out, was willing to say that now energy conservation is just a statistical thing, and in individual reactions it's not conserved. And then Pauli solved it by proposing the neutrino, which it was also, he suggested that there was a fundamentally undetectable particle out there, which isn't a whole lot better, but
But it is better. That is different. That is different, though.
Better. Well, what makes it better is it turned out to actually be detectable.
Right. So.
Now we have a follow-up question.
Yeah. See, so now you can see the questions.
So is anyone doing energy conservation very small sizes? People do. People who do nanotech things do in fact test this. They look at energy budgets and stuff for I have colleagues who study quantum dots and that sort of thing. And you get some weird effects when you start taking things and making them really small, because normally in physics we think about, if you're going to talk about solids, you imagine that it extends infinitely, because when you have a boundary between things, weird stuff happens, and that's kind of messy. You start talking about
messy. That's just like it's not there.
Yeah, you start talking about nanoscale things, then it's mostly boundary, right? It's your cube squared thing that why you can't have a duck the size of a horse, and because the surface area goes as r squared, the volume goes as r cubed. If you make r really small, then you have more surface area than volume, and then things start getting dominated by that surface stuff. But energy conservation as a general principle still works.
But yeah, and things don't. There's lots of things that don't work at the nanoscale, like that we would expect. But we still have conservation of energy and conservation of momentum at the quantum level, right?
Yeah, and not.
There's things we don't have position. We don't have things like. That's what really becomes weird. Things like, where is it? Right, or
it doesn't have a well-defined momentum. It doesn't have a well-defined position, but on average, those things still behave in a nice way. But yeah. So the other thing you mentioned the Rosetta thing, the satellite coming into orbit on a comet, and you were talking this morning about whether people could walk on it, or whether.
Yeah, I mean. This is a cool mission. I mean, if you think about it, one, it's a 10-year mission. Talk about build-up time, but once you start looking at actually getting near a comet, there's a lot of really great, interesting problems that you could explore, because you're on an object that's large enough that you could clearly say there's a gravitational interaction with an astronaut, but small enough that you could jump off of it.
Yeah.
So. It's just fun to play around. I just get out of control sometimes with questions like that. But
yeah, those are fun. So the dangerous thing, I tried to ad lib a problem once in class of like escape velocity from an asteroid sort of thing, which was hampered by the fact that I don't know anything about astronomy. So I was like I was like an order of magnitude too small on the radius, and thus the density was like, just the mass was like 3 orders of magnitude smaller than it should have been. So
you guessed the radius and the mass, or you didn't, or did you guess like the radius and then used a density of rock or something like that?
I guessed the radius, and I said a density of rock is it's like like copper is 10 grams per cubic centimeter or something like that. So I said it's like. It's like that. It's a metal. It's it's 10 times the density of water. We'll go with that.
Literally hand waving.
Yeah, I don't know what the hell. So just to sort of make a point about something and try and do a problem, and then ended up coming up with stupid answers. Then I had to do that. Yeah, okay. So this is why I don't make up problems on the fly.
But the cool thing about Comet 67P is the first thing I did was I wrote a post for the European Space Agency about whether you could just jump off of Rosetta and land on the comet as it passed by. And so in doing that, I needed to know the mass and the size of the comet. And how do you find the mass of the comet? They have a value, but it's funny how these things start off as very, very rough guesses based on lots of weird things. Normally you would find the mass of an object by looking at how other objects gravitationally interact with it. But until you get there, how do you do that? So it's a very roundabout way of finding these kind of things, and that's one of the cool things I like about science. You can't just directly go measure it in the best possible way. You got to, it's like a puzzle. How can I find this without actually doing it?
How can I indirectly get the information that I need? Yeah. Well, that's. I was doing a practice talk this morning because I'm giving a public lecture in Bristol next week in the UK. So I was talking about how dark matter, the discovery of dark matter, is like playing bridge. Because if you're doing astronomy, if you play bridge, you have to try and guess what your partner's cards are based on their answers to what do you bid for this hand, and you can reconstruct that from knowing the conventions of the game. And so astronomy is kind of like that, because all you can ask is how much light comes from this object and what color is the light from this object. But between those two things, you can figure out what it's made of. You can figure out how far away it is. Figure out how fast it's moving. All sorts of stuff, and that ends up leading to dark matter.
Yeah, I think that is the cool part of astronomy, is that we can't go to these stars. We can still find out a whole bunch of stuff about them.
Yeah. There's a great. I think it's a Sidney Harris cartoon, or one of those guys sitting at a desk with a giant telescope behind him, and the caption at the bottom, he's talking to another person, and the caption at the bottom is geologists go on field trips, biologists go on field trips, oceanographers go on field trips. So you don't get to touch any of these things, but you can learn an astonishing amount of stuff.
You can touch the telescope.
Yeah.
Unless it's in space.
So, yeah. Well, you can still touch the one that's in space. It's just a lot harder to get there to do it. But, a handful of people have touched it.
So I sent you a link. I don't know if you saw it. It was John Oliver's show where he talks about native advertising. Did you look at that?
Yeah, I saw that. That got a whole lot of play.
Yeah.
I forget, you were on Science Blogs when the Pepsi thing went down.
Yeah, that's what it made me think of. Let's see. Yeah, there were two. There was a Pepsi Gate, and then there was one other, right?
The Pepsi one is what blew it up.
Yeah.
Somebody else, who was it? Somebody else did it recently. It wasn't Science Blogs, but it was like, I forget, it was Scientific American or.
Oh yeah. Yeah, that's what it was. I think maybe it's Scientific American, but
it might have been Scientific American.
If people aren't familiar, the idea of the native advertising is, people expect stuff to be free online, and they don't want to pay for it, and they don't click on the ads either. So what do you do? And the idea behind native advertising is to kind of make an ad out of content and kind of make them the same. So at Science Blogs, they did they had Pepsi-sponsored posts, right? That was the whole point.
Yeah, well, it was a little bit different, and I think less objectionable than what John Oliver was talking about, which is they created a blog that was scientists employed by Pepsi were going to write about food science things.
Yeah, but they were also promoting Pepsi. They weren't just writing. You can write whatever you want.
Yeah,
right? They were writing with the intent of advertising, or at least promoting.
Or at least they were writing about stuff that they were paid to do for a particular company.
Right.
And
so I mean, that's completely different than what we do.
They never actually posted anything. I mean, the whole thing went pear-shaped so quickly that there were never any actual posts about any science things. There was like a welcome to our new blog. We're excited to tell you about the cool science that we do, under the aegis of the Pepsi Corporation. And then everybody went apeshit, and the whole thing fell apart. And I don't think they ever actually posted anything about science. Or I don't remember seeing anything that gave you any idea what the content was actually going to be.
No.
So,
But I mean, I think it brings in the old problem of, how do you fund things that are, online? And how do newspapers get by? How do, if advertising doesn't work, what do you do? So.
yeah, apparently newspapers used to derive just an astonishing amount of revenue from classified ads, but now things like Craigslist kill that because you can post ads there for free.
I think also with both with newspapers and TV, the idea of how effective these ads were pretty vague. I mean, who knew how many people were reading that or using that to base their decisions? But once you have things online, I mean, you know how many people clicked it. You can kind of tell if people clicked it and then bought something. So you have a better idea that it doesn't really work, probably, and so that makes it less valuable.
Yeah. Yeah, I think the Pepsi thing was a little less objectionable than the stuff that Oliver's talking about, because he was talking about the content that is, it's like posted on the main New York Times site. And it has just a tiny little disclaimer, it's like sort of mixed in with other things. The Pepsi thing was, it was its own separate blog on the Science Blogs Network, which, is marking it a little more clearly than the stuff that they're doing now. But yeah, it's a problem.
Yeah, and I think that there's a fine line between, if you make it clearly advertising, then people don't pay as much attention to it. So I want to make it look like a blog, make sure that people realize that it's not actually a blog, but not clearly an ad either. And otherwise, people just will gloss over it. So there's kind of like a, I want to fit in with this herd of zebras, but I'm not a zebra.
Yeah, there was an interesting thing not that long ago about, Facebook does these things that are, like you get an ad that says, like, Rhett Elaine likes, these sorts of, Crocs footwear or something, which is like, based on one time you commented on, a post, or you clicked on something that was associated with that, and then it uses implicit endorsements from people through things that they maybe clicked once to put ads in front of you, as if those ads were coming from your friends.
Yeah,
which is kind of creepy. But
it's a little creepy, and I mean, again, I don't know is that effective or not, but yeah, it would be where we are 10 years from now in terms of advertising and support for online writing and things like that. So
and how do you? Because it's a real problem, because somehow the people who write stuff need to get paid. Otherwise, they're they can't all have jobs as glamorous jobs as college professors. So how do you get the money to pay the people to make the content? That's a hard problem.
And I don't know how you do it. So, I mean, really, this almost the same is true for writing a book, right? I mean, it's hard to make a living writing books.
Yeah. I mean, people I know who write full time, who just make all their income writing books, tend not to live in inexpensive. I know people who live in sort of rural parts of Ohio and New Hampshire who are, because if they're going to be full-time, freelance fiction writers, that's where you can afford to live as a full-time freelance writer. You're not getting a penthouse apartment in Manhattan on the the salary you make doing fiction writing.
That's for sure.
I mean, and the scary thing is that nonfiction pays way better than fiction writing. We had Jennifer Willett here several years ago. She gave a talk about how she became a physics writer after being she was an English major. So how she got into writing about physics, and talked about the business stuff. And somebody asked about it, and she said, if they're not paying, it's like $1 a word. it's not worth doing. And
$1 a word.
It was,
I'll sign up for that boat.
it was something like that, but you gotta like research a piece, and
that's a good point. It depends on the kind of writing you're doing. If you're just doing BS stuff like I do, I could probably do it for 25 cents a word, right? Because I just make everything up as I go anyway.
Yeah, but science fiction writing, what counts as a professional sale for the Science Fiction Writers Association is 5 cents a word. So if they pay you 5 cents a word, that counts as a professional sale. And people doing nonfiction was like you should be getting 50 cents a word, $1 a word, that kind of scale.
7 cents a word, right?
Yeah, but it's an order of magnitude different.
Okay, well, I'm getting kind of hot here in my garage office.
Your tiny little
garage office.
So you're the dog days of summer, the kids are home being loud.
Well, they're always home, but I don't know. Yeah, it's they get involved in their little things, and you can't quiet them down. It's impossible. They're just better just to get away.
Yeah, that's part of why the forthcoming book has a lengthy acknowledgement of the staff at Starbucks in Niskayuna, where I wrote.
I saw that.
A huge chunk of it because if I'm home, the kids want me to play with them, and if I'm at work, people show up and ask questions about, hey, can I buy some new whiteboard markers? Like, do we need whiteboard markers? Buy whiteboard markers. Don't come ask me about that.
No, see, at work I'm pretty good. No one really bothers me. They just assume I'm wasting my time anyway. So, and they're usually right.
Well, this is heavy lies the head that sits in the chair's office.
Yeah.
Like, I officially have to sign off on all of these purchases, so people will come ask me to sign off on things in advance. I'm like, you're buying $10 worth of whiteboard markers. I don't just buy that. Ask me about that later. So.
Right. All right. Well, it looks like a good place to stop.
Yeah, it's a good place to stop, and then I'm going to be away for a while. So.
Okay. Well, if we don't meet, maybe someone will notice. Maybe someone won't.
Yeah. Well, we did get questions. So.
Yeah.
So and now.
So.
Now you've figured out how to do that, so we can advertise it in the future.
I think what I need to do is figure out how to schedule it so people know about it beforehand. So if they want to participate, they can participate. So.
Yeah. But we're making progress and figuring out this technology stuff.
And it only took 21 episodes. That's not bad.
That's not. It took 300 years to figure out quantum physics. So.
That's right. So we got plenty of time.
Oh God, all kinds of time.
Yeah. All right. We'll see you guys later.
All right. Until next time.
Whatever that is.
Yep.